Welcome back. This is part 3 of this lesson. We're going to continue immediately from the end of part 2, so let's get started. The address resolution protocol is used generally when you have a layer 3 packet and you want to encapsulate it inside a frame and then send that frame to a MAC address. You don't initially know the MAC address and you need a protocol which can find the MAC address for a given IP address. For example, if you communicate with AWS, AWS will be the destination of the IP packets, but you're going to be forwarding via your home router, which is the default gateway, and so you're going to need the MAC address of that default gateway to send the frame to containing the packet. And this is where ARP comes in. ARP will give you the MAC address for a given IP address. So let's step through how it works. For this example, I'm going to keep things simple. We've got a local network with 2 laptops, one on the left and one on the right. And this is a layer 3 network, which means it has a functional layer 2 and layer 1. What we want is the left laptop, which is running a game, and it wants to send packets containing game data to the laptop on the right. This laptop has an IP address of 133.33.3.10. So the laptop on the left takes the game data and passes it to its layer 3, which creates a packet. This packet has its IP address as the source and the right laptop as the destination, so 133.33.3.10. But now we need a way of being able to generate a frame to put that packet in for transmission. We need the MAC address of the right laptop. This is what ARP, or the Address Resolution Protocol, does for us. It's a process which runs between layer 2 and layer 3. It's important to point out at this point that now you know how devices can determine if 2 IP addresses are on the same local network. In this case, the laptop on the left, because it has its subnet mask and IP address as well as the IP address of the laptop on the right, it knows that they're both on the same network, and so this is a direct local connection. Routers aren't required. We don't need to use any routers for this type of communication. Because of this, the left laptop starts using the ARP protocol. Now ARP broadcasts on layer 2. It sends an ARP frame to all Fs as a MAC address, and it's asking who has the IP address 133.33.3.10, which is the IP address of the laptop on the right. Now the right laptop, because it has a full layer 1, 2 and 3 network stack, is also running the address resolution protocol. The ARP software sees this broadcast and it responds by saying, I'm that IP address, I'm 133.33.3.10, and here's my MAC address ending 5B:78. So now the left laptop has the MAC address of the right one. Now it can use this destination MAC address to build a frame, encapsulate the packet in this frame, and then once the frame is ready, it can be given to layer 1 and sent across the physical network to layer 1 of the right laptop. Layer 1 of the right laptop receives this physical raw bit stream and hands it off to the layer 2 software also on the right laptop. Now its layer 2 software reviews the destination MAC address and sees that it's destined for itself, so it strips off the frame and it sends the packet to its layer 3 software. Layer 3 reviews the packet, sees that it is the intended destination, and it de-encapsulates the data, so strips away the packet and hands the data back to the game. Now it's critical to understand as you move through this lesson series, even if 2 devices are communicating using layer 3, they're going to be using layer 2 for local communications. If the machines are on the same local network, then it will be 1 layer 2 frame per packet. But as you'll see in a moment, if the 2 devices are remote, then you can have many different layer 2 frames which are used along the way. And ARP, or the Address Resolution Protocol, is going to be essential to ensure that you can obtain the MAC address for a given IP address. This is what facilitates the interaction between layer 3 and layer 2. So now that you know about packets, now that you know about subnet masks, you know about routes and route tables, and you know about the Address Resolution Protocol, or ARP, let's bring this all together now and look at a routing example. So we're going to go into a little bit more detail now. In this example, we have 3 different networks. We've got the orange network on the left, we've then got the green network in the middle, and then finally the pink network on the right. Now between these networks are some routers. Between the orange and green networks is router 1, known as R1, and between the green and pink networks is router 2, known as R2. Each of these routers has a network interface in both of the networks that it touches. Routers are layer 3 devices, which means that they understand layer 1, layer 2 and layer 3. So the network interfaces in each of these networks work at layer 1, 2 and 3. In addition to this, we have 3 laptops. We've got 2 in the orange network, so device 1 at the bottom and device 2 at the top, and then device 3 in the pink network on the right. Okay, so all I'm going to do now is to step through 2 different routing scenarios, and all of this is bringing together all of the individual concepts which I've covered at various different parts of this part of the lesson series. First, let's have a look at what happens when device 1 wants to communicate with device 2 using its IP address. First, device 1 is able to use its own IP address and subnet mask together with device 2's IP address and calculate that they're on the same local network. So in this case, router R1 is not required. So a packet gets created called P1 with the D2 IP address as the destination. The Address Resolution Protocol is used to get D2's MAC address, and then that packet is encapsulated in a frame with that MAC address as the destination. Then that frame is sent to the MAC address of D2. Once the frame arrives at D2, it checks the frame. It's the destination, so it accepts it and then strips the frame away. It passes the packet to layer 3. It sees that it's the destination IP address, so it strips the packet away and then passes the game data to the game. Now all of this should make sense. This is a simple local network communication. Now let's step through a remote example, device 2 communicating with device 3, and these are on 2 different networks. Device 2 is on the orange network and device 3 is on the pink network. So first, the D2 laptop, it compares its own IP address to the D3 laptop IP address, and it uses its subnet mask to determine that they're on different networks. Then it creates a packet P2 which has the D3 laptop as its destination IP address. It wraps this up in a frame called F2, but because D3 is remote, it knows it needs to use the default gateway as a router. So for the destination MAC address of F2, it uses the Address Resolution Protocol to get the MAC address of the local router R1. So the packet P2 is addressed to the laptop D3 in the pink network. So the packet's destination IP address is D3. The frame F2 is now addressed to the router R1 MAC address, so this frame is sent to router R1. Router R1 is going to see that the MAC address is addressed to itself, and so it will strip away the frame F2, leaving just the packet P2. Now a normal network device such as your laptop or phone, if it received a packet which wasn't destined for it, it would just drop that packet. A router though, it's different. The router's job is to route packets, so it's just fine to handle a packet which is addressed somewhere else. So it reviews the destination of the packet P2, it sees that it's destined for laptop D3, and it has a route for the pink network in its route table. It knows that for anything destined for the pink network, then router R2 should be the next hop. So it takes packet P2 and it encapsulates it in a new frame F3. Now the destination MAC address of this frame is the MAC address of router R2, and it gets this by using the address resolution protocol, or ARP. So it knows that the next hop is the IP address of router R2, and it uses ARP to get the MAC address of router R2, and then it sends this frame off to router R2 as the next hop. So now we're in a position where router R2 has this frame F3 containing the packet P2 destined for the machine inside the pink network. So now that router R2 has this frame with the packet inside, it sees that it's the destination of that frame. The MAC address on the frame is its MAC address. So it accepts the frame and it removes it from around packet P2. So now we've just got packet P2 again. So now router R2 reviews the packet and it sees that it's not the destination, but that doesn't matter because R2 is a router. It can see that the packet is addressed to something on the same local network, so it doesn't need to worry anymore about routing. Instead, it uses ARP to get the MAC address of the device with the intended destination IP address, so laptop D3. It then encapsulates the packet P2 in a new frame, F4, whose destination MAC address is that of laptop D3, and then it sends this frame through to laptop D3. Laptop D3 receives the frame. D3 sees that it is the intended destination of the frame because the MAC address matches its MAC address. It strips off the frame. It also sees that it's the intended destination of the IP packet. It strips off the packet, and then the data inside the packet is available for the game that's running on this laptop. So it's a router's job to move packets between networks. Routers do this by reviewing packets, checking route tables for the next hop or target addresses, and then adding frames to allow the packets to pass through intermediate layer 2 networks. A packet during its life might move through any number of layer 2 networks and be re-encapsulated many times during its trip, but normally the packet itself remains unchanged all the way from source to destination. A router is just a device which understands physical networking, it understands data link networking, and it understands IP networking. So that's layer 3, the network layer, and let's review what we've learned quickly before we move on to the next layer of the OSI model. Now this is just an opportunity to summarise what we've learned. So at the start of this video, at layer 2, we had media access control and we had device to device or device to all device communications, but only within the same layer 2 network. So what does layer 3 add to this? Well, it adds IP addresses, either version 4 or version 6, and this is cross-network addressing. It also adds the address resolution protocol, or ARP, which can find the MAC address for this IP address or for a given IP address. Layer 3 adds routes, which define where to forward a packet to, and it adds route tables, which contain multiple routes. It adds the concept of a device called a router, which moves packets from source to destination, encapsulating these packets in different layer 2 frames along the way. This altogether allows for device-to-device communication over the internet, so you can access this video, which is stored on a server which is several intermediate networks away from your location. So you can access this server which has an IP address, and packets can move from this server through to your local device, crossing many different layer 2 networks. Now what IP doesn't provide, it provides no method of individual channels of communication. Layer 3 provides packets, and packets only have source IP and destination IP. So for a given 2 devices, you can only have one stream of communication. So you can't have different applications on those devices communicating at the same time. And this is a critical limitation which is resolved by layers 4 and above. Another element of Layer 3 is that in theory, packets could be delivered out of order. Individual packets move across the internet through intermediate networks, and depending on network conditions, there's no guarantee that those packets will take the same route from source to destination. And because of different network conditions, it's possible they could arrive in a different order. And so if you've got an application which relies on the same ordering at the point of receipt as at the point of transmission, then we need to add additional things on top of Layer 3, and that's something that Layer 4 protocols can assist with. Now at this point we've covered everything that we need to for Layer 3. There are a number of related subjects which I'm going to cover in dedicated videos, such as network address translation and how the IP address space functions, as well as IP version 6. But in this component of the lesson series, we've covered how the architecture of Layer 3 of the OSI model works. So at this point, go ahead and complete this video, and then when you're ready, I'll look forward to you joining me in the next part of this lesson series where we're going to look at Layer 4.